So let's talk about climate change now and how the volcanoes impact climate change and global warming. Well, first of all, there are some people who claim that the global warming we're seeing is actually caused by the volcanoes. Some people claim that we have lots of carbon dioxide, which is added to the atmosphere from volcanoes, and there is some carbon dioxide. In fact, in the early Earth, we had lots of carbon dioxide in the atmosphere because of volcanoes. So volcanoes, when we have lots and lots of volcanoes, they can contribute to the amount of carbon dioxide in the atmosphere. But today, if we look at the concentrations coming out of volcanoes, it's much, much smaller than the contributions from humans and what we're adding to the atmosphere every year. And so, as we'll see in the next slide, there's actually no noticeable effect of volcanoes on the global trends in carbon dioxide. So we can rule out volcanoes being and impacting the amount of greenhouse gases in the atmosphere today. And the effects of the cooling of the planet, because of these small droplets which form of sulfuric acid, is much, much larger than any warming due to increases in greenhouse gases. So we can prove that by looking at this plot, which we've seen a number of times throughout the course, the Keeling curve, which is basically the rise of carbon dioxide, which has been measured in Mauna Loa on the top of, actually in the top of a volcano in Hawaii, but not an active volcano. And we can see the timing of El Chichon and Pinatubo. And if I remove these arrows, you would not be able to tell me when we had the eruptions of El Chichon and Pinatubo. And so on a global scale, there's no impact on the carbon dioxide concentrations from these two very big volcanic eruptions. And so we cannot blame volcanoes on the rise of CO2 in the atmosphere. So let's go back to the cooling effect of the volcanoes. And again, we have the particles in the atmosphere which have two effects. They actually have a cooling effect at the surface, but they have a warming effect in the stratosphere. And the bottom left plot actually shows data from 1979 showing the temperatures in the stratosphere. So the temperatures between 20, 30 kilometers above the surface. We're looking at the anomalies, the change in the temperatures from normal. And we see these two big rises in temperature, which again are linked to the eruption of El Chichon in 1982 and the rise of the temperatures after Pinatubo in 1991. So we can see that in the stratosphere, we actually have a warming, and if we look at the temperature cycle, when we do have a volcano which impacts the stratosphere, this actually warms the stratosphere. On the right-hand side, we can see that again, we can see different parts of the atmosphere, the impact of Pinatubo. The timing of Pinatubo is given by the green dashed line in June 1991. The top plot shows the changes in temperature, again, changes relative to normal in the stratosphere, in the middle of the troposphere, and at the bottom at the surface. And again, we see and the difference between the colored plots are model simulations of what we expected to happen. These model simulations were done just within a month or so after the simulation, so after the eruption, to show if the models can actually predict the warming in the stratosphere and the cooling in the lower atmosphere. And the black line is the actual observed changes in temperature, again in the stratosphere, the troposphere, and at the surface. And what we see is that the maximum impact of the volcano is actually felt more than a year after the eruption. If we look at the cooling, say at the surface, was in late 1992, more than a year after the eruption in June 1991. Again, it takes time for the sulfuric acid particles to form, and then they have to be spread globally around the planet, north and south, in order to have a global impact on the climate. But when these particles slowly fall out of the atmosphere, then we see that the temperatures return back to normal. But this whole process and the whole impact of the volcano from Pinatubo took about 3 or 4 years until we returned back to the normal situation. So for 3 or 4 years, we had a cooling of the global climate because of this one large volcano and a warming in the stratosphere. If we look at the bottom, this is the simple equation we've spoken about in the beginning of the course of the energy balance, the balance between the incoming radiation on the left-hand side of the equation, which is basically related to the solar constant and the planetary albedo. And on the right-hand side, we have the outgoing radiation, which depends on the temperature of the Earth, and the greenhouse effect, the little T or tau here. What we're actually doing with these natural experiments of the climate system with volcanoes is we're changing the value of the albedo of the planet. If the albedo is normally 30%, then we may be increasing it and going up to 31%. If you change the albedo slightly, we increase the albedo, we decrease the temperatures at the surface. So here's an example of how we can actually understand how the climate works and how by changing the albedo through volcanic eruptions, we can actually change the surface temperatures. So we have many volcanoes that have been studied throughout history, and all of them show the same pattern, that if 0 here is the time of the eruption, we get this global cooling. The amount of cooling will depend on both the size of the eruption, but also the location of the eruption, if it's in the tropics, if it's in higher latitudes. But we see that the maximum cooling occurs more than a year after the eruption. It takes another year or two for all these particles to fall out of the atmosphere. And so 3 or 4 years of the Earth's climate is impacted by these very large volcanic eruptions. Well, because of this cooling, people have also spoken about volcanic winter, dramatic reductions in temperature due to the volcanic eruptions. Some examples, if we're going back in time, even from Benjamin Franklin from 1783, he blamed the very cool summer on the volcanic dust in the atmosphere, which was erupted from the Laki volcano in Iceland. Tambora, 1815, this was a huge eruption, and people claimed that in 1816, the following year, was the year without a summer, that the summer kind of disappeared. It turned into winter in some places. Krakatoa, 1883, the following 4 years after the eruption were much cooler, and the winter of 1888 saw record snowfalls around the world. If we look at 1816, the year without a summer, this followed the eruption of Tambora in 1815. And so we have, this wasn't too far ago, and we have reports and books and paintings even, which we can see what happened after this. We see that there was a very large effect of the cold temperatures in Northern Europe, Eastern Canada, Northeast America. And this was most likely a result of this big eruption, which was the volcanic eruptive index of 7, supercolossal eruption, which occurred in Indonesia in 1815. There were 2 snowstorms in June. June is summer in Eastern Canada and in New England. And there was frost and snow that killed crops in May and June. The lakes and rivers had ice on them in Pennsylvania in the summer of July and August of 1816. But another interesting fact is that this period of the eruption occurred also in what we spoke about before in the week when we spoke about the sun, called the Dalton minimum, between 1790 to 1820, when the sun was a little bit weaker with less sunspots than it is today. And so it could be that a combination of this large volcano and the slightly weaker sun resulted in these very cold temperatures and the year without a summer. If we look at computer simulations of this event, we can see here the summer over Europe in 1816, which were about, the average temperature was about 3-4 degrees cooler than normal. I should point out, when we spoke about heat waves, and we spoke about the massive heat wave in 2003 in Europe, where more than 70,000 people died, that was about 5 degrees warmer than normal that summer. We're talking about here 3 or 4 degrees cooler, so it could be a dramatic impact on the summer of 1816. Obviously, not everywhere on the planet. You can see towards the right, the yellow colors. There were other areas which were maybe normal or even slightly warmer than normal. An interesting story from Pinatubo related to the temperatures is related to the Pinatubo bears, the polar bears. In the summer of 1992, again, this is 1 year after the eruption, the ice on the Hudson Bay melted almost a month later than normal. And the polar bears use the ice to go looking for food. If there's ice on the Hudson Bay, they can go further out looking for fish and for food. When there's no ice, they're stuck to the land where there's obviously no fish. Well, it had a dramatic effect on the population of the polar bears just from this one summer. The bears were bigger, they were heavier, and they had more cubs. And there were more cubs that actually survived through the following winter because there was more food, because we had more sea ice and ice over the Hudson Bay. And so just this, again, one volcanic eruption had a dramatic impact on the population of polar bears in northern Canada. The cubs that were born in that year are called the Pinatubo bears because so many of them survived from that particular year, that class of school. So even today, they're around, and we see that we have this increase in population of polar bears, which were born in 1992, linked to the volcanic eruption in the Philippines. And if we've seen this plot a number of times, which is showing the changes in the temperatures over the 20th century. Again, we know different factors like the greenhouse gases in the top, the red curve, the aerosols, the pink curve, which reflects sunlight, the solar cycle, 11-year solar cycle. But related to this lesson, the blue curve is, again, we see the big drops we have when we have these large volcanic eruptions from Krakatoa in 1883 to Pinatubo in 91. When we put all these factors together in models, we see that this simulates more or less the changes in temperatures we've seen over the last century. And when people talk about the increase in carbon dioxide over the last 100 years and that it doesn't match the increase in the temperature plots, well, it shouldn't match the increase in temperature because there are other factors which impact the global temperatures, like volcanoes. And the big dips we see here in the plot of temperature at the bottom are because of the large volcanoes we've had in the last 100, 150 years. And so we have to take all of these factors into account when we're talking about changes in temperature over time.